Again, good afternoon. Welcome to the third Chancellor's Lecture Series event for this academic year. This event, titled Chip War, Computing Power and the U.S.-China Competition. Today, Chancellor Lewis, the WDT teaching team, and I have the pleasure of welcoming Dr. Chirs Miller. I'll formally introduce him in just a few minutes. The content of his recent book, Chip War, and today's discussion supports multiple NDU, CIC, and WDT learning outcomes to include the evaluation of cyberspace capabilities in the achievement of national security goals and the identification of implications from emerging and disruptive technologies on the changing character of war. So if you've had the opportunity to browse Chip War, you probably found several aspects quite interesting. A couple of things that stuck out to me is the reoccurring character of William Perry. Long before he served as Secretary of Defense, Perry was instrumental in detecting and advancing missile technology with chips. It just so happens that NDU is also the home of the William J. Perry Center for Hemispheric Defense Studies. The book also includes a short chapter on how a potato executive helped to revive America's computer chip industry in the 1980s. And he did that by investing in an Idaho company that specialized in DRAM chips. So as a nod to that chapter, I brought some potato chips here. Feel free to grab some on your way out, but please, no eating in the auditorium. And the New York Times review that you probably read describes Chip War as a non-fiction thriller, one that makes a whale of a case, that the silicon chip industry now determines both the structure of the global economy and the balance of geopolitical power. So with that, I'll now give you the standard introduction. Chirs Miller holds multiple academic positions, to include Associate Professor of International History at the Fletcher School of Law and Diplomacy at Tufts University. He is the Jeane Kirkpatrick Visiting Fellow at the American Enterprise Institute, and he is the Eurasia Director at the Foreign Policy Research Institute. At the Fletcher School, he teaches courses on U.S.-Russian relations, Russian foreign policy, and the history of U.S. foreign relations. And without further delay, thank you for your patience. Please join me in extending a warm welcome to Dr. Chirs Miller.
Thank you very much for the invitation to join you all today. Delighted to be here to share some conclusions from my book and what it means for U.S.-China competition across multiple different spheres. I hope you'll come away at least understanding some of the differences between potato chips and computer chips and perhaps something beyond that as well. During the Reagan administration, there was an economist who worked in the White House who was alleged to have asked once, potato chips, computer chips, what's the difference? And so I hope I can convince you that, in fact, there is some pretty crucial differences between the production of both of those types of chips, important though both of them are. I began this project not intending to write a history of the semiconductor industry. I'm a Russianist by training. My previous 3 books have been on different aspects of Russian history, politics, foreign policy, and economics. And I started 8 years ago planning to write a history of the development of military technology during the Cold War. And the question that motivated me at the outset is, why was it that during the Cold War the Soviet Union could produce all of the key military technologies of the early Cold War, like atomic weapons and long-range delivery systems, but by the end of the Cold War had struggled to keep pace with the United States and its allies? And as I dug into that question, it seemed to me that computing technologies were at the core of the answer. Not just any specific type of military system, but computing that was distributed across different military systems that helped them communicate together, to acquire new sensing capabilities, to understand all the new information that defense systems were getting, which then raised another puzzle. Well, why couldn't the Soviet Union do that too? They had lots of smart physicists, lots of investment in their military R&D programs, and yet the United States jumped far ahead in terms of its computing capabilities by the end of the Cold War, such that when the U.S. military arrived in the Persian Gulf War in 1991, it stunned both itself and the rest of the world with its ability to deliver weapons with extraordinary precision in a way that ended the war far more rapidly than almost everyone in Washington and also in Moscow thought possible. And it seemed to me that semiconductors were at the core of this shift in military power, because semiconductors are the device that makes all modern computing possible. And as I was doing this research into the evolution of military technology, we were learning in real time the extent to which the rest of the economy was dependent on semiconductors too. The last couple of years of semiconductor shortages have illustrated that chips are not only important for smartphones or for PCs or for data centers, but also for dishwashers and coffee makers and automobiles. Indeed, the entire economy today really can't function without access to semiconductors, which provide the computing power, the memory capabilities, the sensors, and the communications that all manner of devices rely on today. And so what I'd like to suggest to you is that you can't understand the modern world without putting semiconductors at the core of your story, and you can't understand either the trajectory of the global economy or of the balance of military power without looking at the role that semiconductors have played in the past and will increasingly play in the future. Now, what is a semiconductor? Perhaps to start, for those of you who haven't done PhDs in electrical engineering or material science, as I indeed had not done when I started this book, it's a piece of silicon, often the size of your fingernail, with thousands or often millions or even billions of tiny transistors carved into it. A transistor is just a switch that turns a circuit on or off. When the circuit's turned on, it produces a 1. When the circuit's turned off, it produces a 0, and all of the ones and zeros undergirding modern digital computing, all of the data processed on your smartphone or PC, all of the data remembered on your devices is all just ones and zeros produced by circuits flipping on and off on tiny silicon chips. And in order to fit a billion, or in the case of a cutting-edge smartphone, 15 billion tiny transistors on a small piece of silicon, these transistors need to be extraordinarily small. And today, the most advanced transistors of the type that are in your smartphone are measured just by a number of nanometers. They'll often have features just a dozen or so nanometers wide or tall, which means that each of the transistors on your smartphone is smaller than the size of a virus. And they're produced with almost perfect accuracy, billion by billion, powering the smartphones and PCs and data centers that we all rely on. The process of manufacturing transistors by the billions with basically perfect accuracy is the hardest manufacturing process humans have ever undertaken. There's nothing we've produced more of in the world than transistors. In fact, we've produced more transistors just in the last year than the combined quantity of all other goods produced in all of human history. Nothing else comes close. And to produce billions of transistors at nanometer scale, that's billionths of a meter in terms of scale, requires a complex supply chain that stretches from Europe to the US to Japan to Taiwan, where today Taiwan produces over 90% of the world's most advanced processor chips, including chips in your smartphone, likely chips in your PC, and chips in all of the data center and telecom infrastructure we rely on. And in addition to producing 90% of the most advanced processor chips, Taiwan also produces over 1/3 of the new computing power the world adds globally, which means that Taiwan isn't simply important for its geostrategic implications, it's also important because the world economy would freeze if we lost access to computer chips produced in Taiwan, where one company, the Taiwan Semiconductor Manufacturing Company, is both the world's largest and the world's most advanced chip maker, and today almost all of their chip making capacity is on a small island just off the shores of China, which makes the chip industry important not only because it will define the future of US-China competition in terms of chips' relevance for military uses, for intelligence uses, for the broader economy, but also because the production of chips is deeply intertwined with the geography of US-China competition. And indeed, the island that is most likely to be the source of a potential future crisis between the United States and China is also the island that produces all of our most advanced processor chips, which of course is a situation of extraordinary risk that we and the rest of the world find ourselves in today. So Taiwan produces the most advanced chips in the world today, but it does so taking advantage of a supply chain that stretches across many different countries. And if you want to manufacture an advanced semiconductor today, you need to start before the manufacturing process with designing what your chip is going to look like. And a chip that has 15 billion transistors on it is extraordinarily difficult to design. You can't design that by hand. There are just too many components. You need to access specialized software tools that are produced just by a couple of companies all in one country, the United States, which has almost a monopoly on the production of the software tools needed to design semiconductors. Once you've got access to design tools, you need to actually undertake the design of semiconductors. And although semiconductors have the same basic structure, the designs are very diffuse. A chip designed for communications purposes will be very different from a chip designed for sensors. A chip in a smartphone will be very different from a chip in a data center. And so there's a lot of unique, specialized knowledge that the companies that design chips have inside of their companies and their employee base. And most of the most advanced chip design firms are based in the United States. Companies like Apple, which is one of the world's most advanced designer of chips in smartphones and in PCs. Companies like NVIDIA, based in California, which designs almost all of the chips used for training AI systems in data centers. Companies like AMD, Qualcomm, and others play a leading role in the chip design business, even though most of those firms do all of their manufacturing in Taiwan. Once you've got your chip design, you need to acquire the machine tools and the materials needed to manufacture advanced semiconductors. And because of the extraordinary precision involved in manufacturing billions of components at virus size scale, the machine tools needed to make chips are the most complex machine tools ever invented in human history, with really nothing else that comes close. To make an advanced chip, you need lithography tools that shine rays of light through very precise patterns to carve shapes into your silicon chip. You need deposition tools capable of depositing thin films of materials just a couple of atoms thick on your piece of silicon. You need etching tools that can etch tiny canyons just a couple of atoms wide to create the shapes of the 15 billion transistors that make your smartphone work. And these machines are extraordinarily complex to make themselves, drawing on very sophisticated international supply chains. And I'll just describe one of these machines to you to illustrate the amount of precision involved. The first and most important step in chip making is called photolithography, carving or printing shapes with light. And today, if you want to make an advanced semiconductor, you need to not just use visible light, because visible light is far too broad a brush with which to paint the tiny shapes on advanced chips. You need light with a wavelength of 13.5 nanometers, the most precise wavelength of light we can produce at scale, which is used to carve shapes into advanced chips today. And producing light at a wavelength of 13.5 nanometers is extraordinarily complicated. There's just one company in the world that knows how to do it, ASML, based in the Netherlands, the largest tech company in Europe by market capitalization, which has unique capabilities to produce light with the requisite wavelength. And here's how you do it. You have a ball of tin, 30 microns, millionths of a meter wide, falling through a vacuum. You pulverize it twice with one of the most powerful lasers ever deployed in a commercial device. The light explodes into a plasma measuring 40 times hotter than the surface of a sun. The plasma emits photons at just the right wavelength, which are then collected by the flattest mirrors humans have ever made and then directed towards the silicon on which your chip is being carved. Undertaking this process of engineering is brutally expensive. Each one of these machines costs $150 million a piece, making them the most expensive machine tools in human history. They require multiple 747s to transport. They require personnel from ASML, the company that makes them, to be on site for the life cycle of the machines, and there's only one company in the world that knows how to do it. And that's just one of the machines you need to produce advanced semiconductors. The other machines that I've described that deposit or that etch shapes on semiconductors are scarcely less complex. And because it's so complex, because the engineering is so precise, and because the skills needed to build these machines are so unique, the companies that know how to do it have almost monopolistic positions in the supply chain. You can't make an advanced semiconductor without acquiring machines from 5 companies, one based in the Netherlands, 3 in California, 1 in Japan, without which it's simply impossible to make advanced chips. And these companies have been in their market positions for decades, in some cases even for half a century. And although all of the most advanced chips are made in Taiwan today, the tools that make those chips are imported into Taiwan from Japan, the United States, and the Netherlands. So the chip supply chain stretches from the Netherlands to the United States, Japan, all the way into Taiwan, and that's not even discussing the ultra-purified materials, the silicon wafers, and gases that are needed to manufacture semiconductors. There's really nothing else in manufacturing that comes close to the complexity involved, because there's no other type of manufacturing that is anywhere close to the precision and ultra-low fault tolerance that making semiconductors with billions of components necessitates. Now, the international supply chain that I've just described to you is a triumph of human efficiency. It has produced advances that have made possible the distribution of computing power across society. You can't live an hour of your life unless you're asleep without touching multiple semiconductors, usually hundreds or thousands of semiconductors. And although almost none of us have ever bought a semiconductor, all of the devices we rely on have dozens or hundreds or thousands of semiconductors embedded inside of them, and that's because chips today are both more powerful and cheaper than ever before. And in 1965, in the early days of the chip industry, Gordon Moore, who is an inventor, a chemist, and one of the founders of Intel, one of the leading chip firms in the US, noticed that the amount of computing power on each chip was doubling every single year. And that relationship came to be known as Moore's Law, and Moore predicted it would last for at least a decade, all the way through 1975. And in fact, it's lasted all the way up to the present. Roughly every 2 years, the amount of computing power per chip doubles. We find ways to fit twice as many transistors on chips because we've shrunken down transistors from the point where they were visible, which is what they were in the early days of the chip industry, to the virus-sized transistors that make possible computing on smartphones and PCs today. And that's only been possible because we've built these extraordinarily complex and precise supply chains that have both produced more advanced chips and chips that have lower cost for the computing power they provide than ever before. There's no other segment of the economy, no other segment of technology that has progressed with anything close to the rate of Moore's Law. Nothing else doubles every 2 years. I like to think about what life would look like if airplanes flew twice as fast every 2 years. It's sort of impossible to conceive how fast they'd be going. I think it'd be near the speed of light by this point. But semiconductors have done it. Year after year, they've delivered on the promise of exponential growth, which is why the first commercially valuable chip sold in the early 1960s had 4 transistors on it. And today we're at 15 billion for the chip inside of your smartphone. That growth rate is simply unparalleled by any other technological trend line, any other part of the economy. So in some ways, the chip industry is an extraordinary success, a triumph of human ingenuity, a benefit of globalization that's allowed the efficiencies that have made this industry and its extraordinary advances possible. But in other ways, as I've alluded to already, there's deep vulnerabilities embedded in the way the supply chain is structured today. And in particular, our reliance on semiconductors that are manufactured in Taiwan is an extraordinary vulnerability, particularly given the growing Chinese threat to that island. In addition to that, there's a growing vulnerability in the fact that America's advantages relative to its adversaries have been declining in recent years. It used to be the case even a decade ago that the US and its allies were far, far ahead of any potential adversaries when it came to the ability to produce the components that were necessary to develop computing power, both chips used for computing, chips used for memory, chips used for communications and sensors. The US used to have a vast lead over adversaries like Russia and China, but since 2014, the Chinese government has identified semiconductors as an extraordinary vulnerability that they face. And it's understandable why the Chinese think they're vulnerable when it comes to semiconductors, because today, this year, like every year for the past decade, the Chinese government has spent as much money importing chips each year as it spent importing oil. There's no product on which China is more reliant, and that's because China can't currently make the most advanced semiconductors at home. It has to import them almost exclusively from China's adversaries, Taiwan, Korea, Japan, and the United States. And so since 2014, Xi Jinping and other Chinese leaders have identified as a priority finding ways to build up China's capabilities to domestically produce chips, building up Chinese champions that can produce chips comparable to what are designed by US firms and manufactured in Taiwan. And as part of this industrial policy program, China has been spending tens of billions of dollars a year in subsidies at the national level as well as at provincial and local levels to build up China's chip industry, acquire new technological capabilities, and establish firms that can compete globally in the production of advanced semiconductors. And over the past decade, China has made some real strides when it comes to its chip industry. Certain types of memory chips, for example, China has reached the cutting edge in terms of production. When it comes to manufacturing processor chips, China is still meaningfully behind Taiwan, but it's much less far behind than it was a decade ago. When it comes to designing certain types of chips, like the chips that go into smartphones, Chinese companies have proven themselves just as capable as American firms like Apple or Huawei. And so the gap in aggregate between US capabilities and Chinese capabilities has narrowed substantially over the past decade. And that's important not only to smartphone makers and PC manufacturers, although it's very important to them, it's also important because of the strategic and the military ramifications. Because as I suggested at the outset, there was a deep relationship during the Cold War between America's computing capabilities and its intelligence and military capabilities that flowed from that. It's always been the case that intelligence has depended in no small part on computing power, whether it's the British computers during World War II that cracked Nazi codes at Bletchley Park, or American anti-submarine warfare efforts in the Cold War, which funneled undersea sound data into the most advanced supercomputers that the United States was able to deploy, or the fact that the National Security Agency and the Soviet KGB both had privileged access to their country's most advanced supercomputers. There's a direct relationship between intelligence and computing power, because computing is all about acquiring data and making sense of it, and that's exactly what intelligence agencies do too. And so if you accept my claim that historically computing has been at the core of the race to develop and deploy intelligence capabilities, I think it only holds that over the next several decades, that relationship will remain important and probably even become more important in determining which countries have the most advanced intelligence collection and processing capabilities. And similar for military systems, I think there's no doubt that computing will be at the center of next generation military technologies too. It's not just the question of can we deploy computing to specific military systems. It's also can we collect data, make sense of data, network more and more devices together, and use computers to design more effective systems. This has been something the U.S. military and the defense industrial base have been doing to a large degree over the past several decades, but its importance is only growing, and especially as we begin to think about the application of semi-autonomous systems into military environments, the role of computing only grows. If you want to train a system to act autonomously or semi-autonomously, you do so in a data center. Data centers are where autonomous systems are created. And just like you need a very advanced data center to teach a car to drive semi-autonomously, you also need a very advanced data center to teach a drone to fly semi-autonomously. And so in no small part, I think the capability of future semi-autonomous military systems will depend on the quality of the data centers in which they're trained. And data center quality is basically a function of how advanced are the chips that you have inside of them, which is why last year the Biden administration released a sweeping new set of export controls that limit the ability of China to acquire the most advanced chips for training AI systems in data centers, which are designed by US firms and manufactured almost exclusively in Taiwan. Up until last year, it was legal for Chinese firms to import AI chips from the United States, so long as they were supposed to be used for civilian purposes. There was plenty of open source reporting of ways in which ostensibly civilian chips were being deployed to military uses, but the core problem is that the exact same chips that can train cars to drive can train drones to fly. There's no way of differentiating between the different types of chips. It's just a matter of knowing how they'll be used, and the US concluded, I think justifiably, that it had no idea how chips were being used once they were entering China. And so now it's illegal to import the most advanced chips for training AI systems into data centers to China, precisely with the goal in mind of limiting China's ability to train more advanced systems for use in intelligence and in military systems. So the Biden administration is betting that computing power will be at the center of strategic competition, given its use for intelligence and next-generation military systems, and the Chinese government is making the exact same bet. The Chinese military has been open in its belief that the application of intelligence to military systems will be central to the future of warfare. We know less in open source discussions of how the Chinese intelligence agencies think about this question, but I see no reason to doubt that they've drawn similar conclusions about the necessity of acquiring lots of data and therefore the means to process that data. So there's an arms race going on right now in computing technologies, which means that there's an arms race in semiconductors. And if you think like I do that a key component to the quality of next generation systems will be the computing capabilities we've used to train them, the arms race in semiconductors may well be as important as the race to produce any given type of system, because chips will go into training all types of systems. It's a critical component across all of the different types of capabilities we'd like to harness and deploy over the coming decades. And because it cuts across all of these different spheres, semiconductors are at the core of both how China and the United States perceive the competition. Now, the U.S. benefits from the fact that today, although the U.S. is far from capable of producing advanced chips on its own, it relies on machines from the Netherlands and Japan, manufacturing in Taiwan. Almost all of the process steps for making an advanced semiconductor are in the hands of either U.S. firms or firms and close allies or partners, whereas China can do almost nothing in the sphere of semiconductors that can't also be done by other countries. So in terms of pure capabilities, the US and its allies are meaningfully ahead of China, even though the gap has narrowed. But in terms of where the manufacturing and assembly happens, much of it happens in East Asia, and especially in Taiwan and in China. And here I think is the source of much of the risk we face today. Our computing capabilities, both for civilian uses, but also to no small extent for government uses, are produced in East Asia, in Taiwan, and often assembled and packaged in China, which both presents security risks. Do we have the knowledge we need of how they're manufactured, whether they're manufactured the way we believe they're being manufactured? And it presents risks that in case of a crisis, we might lose access to the chips that we require. In economic terms, it would be a disaster if we were to lose access to chips made in Taiwan. It'd be very difficult to produce a smartphone anywhere in the world the next year if we didn't have access to chips made in Taiwan. PC production would fall easily by a third, perhaps by half. Data center rollout would grind to a halt. We wouldn't have any AI chips. It would take months, if not years, to find alternative sources of supply. Modern cars have 1,000 or so semiconductors inside of them, many of which are made in Taiwan. It would be a disastrously messy process to find ways to source the chips needed for auto production from non-Taiwanese sources. And that's to say nothing of the dishwashers and the microwaves and the coffee makers that also rely on semiconductors that are simple, but many simple semiconductors today are made in Taiwan, and there's not much spare capacity if we were to lose access to Taiwan, given the extraordinary amount of capacity that exists in Taiwan. So there's a huge risk hanging over the world economy, the world tech sector, and also the U.S. government's ability to access the chips it needs if we were to lose access to Taiwan's chip production. And so the U.S. government and U.S. companies are beginning to think about ways to disentangle themselves from this dilemma. The CHIPS Act was funded last year with the aim of boosting chip making in the United States, which is a worthy goal. It's something that I think is important, but I think we should be realistic about how difficult it will be to begin to disentangle ourselves from manufacturing in Taiwan and assembly in China. The reality is that the U.S. economy in aggregate, including microelectronics that the U.S. government relies on, is deeply, deeply intertwined with both Taiwan and China, and the process of disentangling will cost many billions of dollars over, I think, at least a decade to find ways to do that. And it's not so simple to say, let's decouple, as voices in Congress occasionally advise. You can do that, but the price tag will be in the hundreds of billions of dollars over the next decade, a price tag that, so far as I can tell, American consumers thus far are unwilling to bear. So the challenge we face right now is to find ways to address the security risks in microelectronics, both economic security, the prosperity that chips make possible, and also more traditional forms of security, the chips that our government systems, intelligence, and military systems rely on, but to do so in a way that is actually viable in terms of how much it will cost. And that requires, I think, a strategy for selective decoupling in electronics that we're just beginning to understand. Right now, we've seen U.S. firms and the U.S. government begin to think through what would it require to have non-China supply chains for critical microelectronics. And what we find at every turn is that it's far more difficult than we would like. It's far more difficult than we would like because there are Chinese-based components in almost every type of system. And as the manufactured goods we acquire, especially in electronics, get more and more complex, it's harder and harder to guarantee that one component won't be sourced from China. And particularly given China's central role in the production of the world's electronics today, there are many types of goods where it's hard to find non-China sources of supply. So simply advising decoupling without being willing to pay a very expensive price tag, I think is not a viable strategy. And instead, we need much more targeted approaches to identify what's the threat that we face and what's our realistic pathway to finding ways around a reliance on Taiwan and China. There are alternatives. There's certainly chip making in the United States and in more secure locations like Korea, Japan, and Europe. There's assembly facilities outside of China, although I'm not sure Vietnam is that much more secure if you're worried about military escalation scenarios. And so the fact that the world's smartphone manufacturers are moving their smartphone production from China to Vietnam strikes me as perhaps missing a glance at the map. But I think the reality of this assembly dilemma shows just how complex any sort of decoupling strategy will be. And so as we try to think our way through this challenge, the reality we've become far too dependent on chip making in Taiwan, far too dependent on assembly of electronics goods in China, and that the price tag for restructuring supply chains will reach to the many tens of billions of dollars and probably hundreds of billions of dollars over the coming years. Clear strategic thinking about how we do this in a cost-effective and a politically viable way, I think, is absolutely central to addressing the semiconductor challenges that we face. In addition to that, I think there's one final point to underscore. Certainly there are extraordinary risks involved, and we've seen the U.S. government focus on risks a lot over the past several years, risks that have been addressed by export controls, risks that are being addressed by efforts to restructure supply chains. But next to the risks, we've also got to think about the reality that American prosperity and security have been primarily guaranteed not by risk mitigation, but by the fact that Moore's Law has raced ahead and given us a tremendous advantage over our adversaries. The reason that the U.S. is so far ahead in semiconductor technologies in collaboration with Taiwan and Japan and Europe is not primarily because we've been really good at stopping adversaries from learning our secrets, but because the cutting edge races forward so rapidly that it's just extraordinarily difficult for adversaries to catch up. The fact that Moore's Law has continued with very few changes over now 60 years is a great benefit not only to the U.S. economy but also to the U.S. strategic position. And the fact that the innovations that have driven Moore's Law have happened largely in the United States have made possible many of the advantages in intelligence capabilities and in military capabilities that I've described. And so next to the agenda of risk mitigation, we've also got to add a second more important point, which is that fundamentally we need to make sure that Moore's Law survives and continues well into this century, because U.S. prosperity over the last half century has depended on it. U.S. security has depended on it. And I think looking forward, U.S. strategy depends not only on us staying ahead of China, but of us staying ahead of China because we're able to harness the advances that Moore's Law produces. And so as we think about the risks and the opportunities associated with microelectronics and semiconductors, I think next to the desire to hold back Chinese advances, we've got to focus just as much and probably far more on the effort to make sure we've got an environment that is conducive to ensuring that the next generation of semiconductor technologies continue to race ahead in the United States. So with that, I'll wrap up my comments, but we welcome any thoughts or questions that you have.